Sorry, I'm kidnapped, so I have to go and take care of my children. Take them to school and stuff like that. Should it be?
Yeah.
Good morning once again, students. I hope we are ready for today's lecture. So in our last lecture, we have looked at how to determine the equilibrium constants if we're able to get the equilibrium concentrations of all the species involved at equilibrium. We've also looked at the characteristics of the equilibrium constant vis-a-vis the relation between the equilibrium constants and the stoichiometry of the reaction. Okay, so today we're looking at equilibrium process involving gaseous species. It is much easier to determine the pressure of a gas than to determine the molar concentration. For example, the few illustrations we've taken in our previous lecture, where we at the reaction between hydrogen and fluorine to give hydrogen fluoride, which are all gaseous species. Yes, we've determined the equilibrium constant in terms of concentration. However, like I said, for gaseous species, it's much easier to determine the concentration in terms of partial pressure. Because if we assume that the reaction is, the gases are ideal gases. If we assume that the gases are obeying ideal gas equation, you can see here, the ideal gas equation says that PV is equal to nRT, all right? So we can write that P is equals to N over V RT. Now, N over V here is the number of moles per volume. Number of moles per volume is exactly equals to concentration. So we can write therefore that P is equals to concentration times RT. Now, what it means is that the pressure is directly proportional to the molar concentration. So instead of measuring the molar concentration, if you're able to measure the pressure, it will be easy for us to determine the equilibrium constant involving such process. Now, let's take, for example, in this case, we are looking at the synthesis of ammonia formed from the combination of hydrogen and nitrogen. Nitrogen, a gas, hydrogen, a gas, and of course, the product of the reaction is also a gas. So let's see what happened. Now, if we write the equilibrium constant in terms of concentration, as I've written here, taking the stoichiometry of the reaction into consideration, we have that the equilibrium constant will be equals to the square of the concentration of ammonia, which is the product, divided by the product of the concentration of nitrogen and the concentration of hydrogen raised to the power of 3. Now, if the gases involved here are behaving ideally, we can use the assumption by substituting for concentration in the ideal gas equation. Now, in the ideal gas equation, we have written that P is equals to, P is equals to C, let's call it Pi now. Pi, that's the pressure of individual species. Ci, the concentration of individual species, RT. Okay, then this will imply that the concentration of individual species will be equals to Pi over RT. So wherever we see concentration in this expression, no, Okay, don't worry. All right, so whenever we see concentration in this equilibrium expression, let's put pi over RT there. Now, in this case, now we're looking at, so we can say that the pressure of ammonia will be equals to the constant. All right, let me put this, sorry. Let's clear this. All right, so we can write that the concentration of ammonia will be equals to the pressure of ammonia over RT. Similarly, the concentration of nitrogen will be equals to the pressure of nitrogen over RT. And of course, the concentration of hydrogen will be equals to the pressure of hydrogen over RT. So if I put all this into this expression here, what I'm going to have there is that this becomes, instead of concentration of nitrogen, of ammonia now, I'm going to put this. So I'm going to have P NH3 over RT all square divided by P concentration of N2, N2 rather, over RT multiplied by P of H2 R over RT raised to the power of 3. Okay, so that is what we have here. So if we rearrange this, so we are saying that K will be equals to, I'm coming from here now, so I can write this as P square of ammonia over RT square divided by P N2 over RT times P H2 over RT all cube, all raised to the power 3. So you can close the bracket. All right, so this of course becomes, and that's what we have here. So we can write this as, let me erase what I've written so far. It's also already displayed, but I want us to have a real-time derivation. That's why I'm writing all this. I don't want to rush it. All right, so let's erase all this now. Okay, erase all. So we can write, therefore, that K will be equals to P NH3 squared over P N2 multiplied by P cube of H2 now, all multiplied by, now we have, so we're going to have here RT raised to the power of 4 minus 2. Where do we get the 4 from? If you are following, you see from here that this is RT, this is 1 over RT squared, and that's what you have here. 1 over RT, that's what you have here. Here you have 1 over RT, then you have 1 over RT cube. So 1 over RT multiplied by 1 over RT cube give you 1 over RT raised to the power 4. Okay, and of course 1 over RT squared divided by 1 over RT raised to the power 4 will simply be equals to RT over 4 over RT squared. I mean, this is just ordinary arithmetics that we taught in secondary school. So this, of course, simply becomes K. Now, all the terms here are in terms of partial pressure, all the terms here. And of course, it reflects the stoichiometry of the reaction, because don't forget the equation is N2 plus 3H2 going to 2NH3. All right, so that is a reflection of the pressure, the stoichiometry of the reaction, pressure of ammonia raised to the power of 2. That's the stoichiometric coefficient of ammonia, pressure of nitrogen raised to the power 1, and that of hydrogen raised to the power of 3. Okay, so this that I've circled is what we call equilibrium constant in terms of partial pressure, Kp. And this is equals to RT. Now, let's have a look at this carefully. Here, the number of moles here is 2. The number of moles here is 1 plus 3. That is 4. So we have 4 to 2. Okay? And the change in number of moles, therefore, will be equal to number of moles of products minus number of moles of reactants. In this case, it's going to be minus 2. Okay, so this is equals to sorry, please. Sorry, let me clean this again so we don't get confused. Just so that is my opinion. Yeah. It's okay. All right. Now, let me go back again to it so that we don't get confused. So we are saying that for this reaction, you have here. So let me write it again. So what we have here is Kp, or rather Kc, is equals to Kp RT 4 minus 2. Now, that is equals to Kp RT squared. All right, so that's what we have for the ammonia. Okay, I can use my hand to clean. That's okay. So that's what we have for the equilibrium constant in terms of partial pressure for ammonia. Now let's look at the next slide. Now, let's look at this reaction here. Just as we have argued for the ammonia synthesis, we have H2 plus I2 to give us 2 moles of HI. Okay, 1 mole of hydrogen, 1 mole of iodine to give 2 moles of hydrogen iodide. So we have 2 moles of gaseous reactant, 2 moles of gaseous product. In that case, RT delta N will simply be equals, since delta N is equal to 0, that will be simply equals to 2 minus 2, which is equals to 0. All right. So for this case, the Kc is exactly equals to Kp because RT is raised to the power of 0, NT raised to the power of 0 is equals to 1. Okay, so that makes this easy for us to get. Now let's now look at an hypothetical case. So we've used ammonia, we've used hydrogen iodide. Now let's look at a general case, a general hypothetical case where you have A of A and reacting with B of B at equilibrium with C of C, and of course D of D. Let me write what we have here for you. So what we have here is A of A plus B of B at equilibrium with C of C plus D of D. Okay, so the sign is missing here, the equilibrium sign is missing here. How do we establish the relationship between Kp and Kc for this reaction? Okay, just like we have done. Okay, let me quickly go through that with us. I think I should have a blank space. Mm. That's pressure, pressure. Hey, this is all right. So, all right. So let's all right. So let's uh try to. This is what. Sorry. Hey, I don't see the pen again. All right. Okay. Now this is what I'm trying to explain. Let me write the equation. So we have A of A plus B of B at equilibrium with C of C plus D of D. Now let's say the partial pressure of A, okay, let me say the concentration of A will be equals to PA over RT. Similarly, concentration of B will be equals to PB over RT. And of course, the concentration of C will be equals to PC over RT. And concentration of D will be equals to PD over RT. Now, the equilibrium constant expression for this reaction, Kc, will be equals to C of raised to the power of C, D raised to the power of D over A raised to the power of A, and of course, B raised to the power of B. If I substitute for the concentration terms, I'm going to have here so I want to put my phone in silent so that it won't be an hindrance. Okay, so let's continue. So we can have here PC over RT raised to the power of C dot PD over RT raised to the power of D divided by PA over RT raised to the power of A multiplied by PB over RT raised to the power of B. And this, of course, becomes PC raised to the power of C multiplied by PD raised to the power of D multiplied by 1 over RT raised to the power of C multiplied by 1 over RT raised to the power of D divided by PA raised to the power of A multiplied by PB raised to the power of B dot 1 over RT raised to the power of A, and of course 1 over RT raised to the power of B. Now this becomes, now all the terms here stands for the equilibrium constant in terms of partial pressure. So let's say this is Kp. Now let's now deal with this this constant. All right, this is so this of course becomes let's see what that's going to give us. That should give us 1 over RT raised to the power of C plus D over 1 over RT raised to the power of A plus B. Okay, and of course that becomes, let me write it here. I want to have enough space for writing. All right, so permit me to continue here so I can have space. So let me move it here. So we have that Kc is equals to Kp. Now, let's deal with this now. This will be multiplied by RT A plus B minus C plus D. I want to believe everybody know how I have done this. Okay, so I'm dividing this by this. So this will go up, and of course this will be the denominator. I'm sure you remember that kind of a thing where we have let's say A over X divided by B over Y, and of course that becomes A over X times Y over B. Okay, so I'm sure you know this. All right, so that's what I've done here, so that you can understand what I've done. That's why I'm explaining it. So this is this equals to, please. All right, so Kc therefore will be equals to Kp RT. Okay, I'm just writing what I've written before. A plus B minus C plus D. Now, what's the meaning of all this? Let's come back here. We will say from this equation, the total number of products is equals to C plus D. While total number of reactants is A plus B. Now, what we have done here is change in N will be equals to NP minus NA. N reactant, sorry, not A. This is reactant, this product. So change in number of moles will be total number of moles of products minus total number of moles of reactant. Okay, that's what this stands for. Now, if you look at this now, this is number of moles of reactant, and this number of moles of product. But what we have here as delta N is number of moles of product minus number of moles of reactant. So therefore, this is simply equals to Kp RT minus delta N. I'm sure that should be clear. Let me explain it again so that for some of us that may not get what I've just explained here, let me quickly explain it again. We are saying the number of moles of products is equals to C plus D. Total number of moles of reactant is A plus B. All right. The change in number of moles normally will be equal to number of moles of product minus number of moles of reactant, which of course should be equal to C plus D minus A plus B. But what we have here is A plus B minus C plus D. So if I put minus A, so what we are saying in essence is that what we have is actually minus delta N. I'm sure that is clear to all of us. So at this point, at this junction, I would like us to log in again and submit the attendance. All right. So the codes are okay. The first code. So let's start with the first one. Is T6VN8. T6VN8. That's the code. The first code. The other code will be given in the course of the lecture as we continue. Okay. So let's make progress. All right, so let's see. This question says, let's try to use a question to illustrate all we did so far. The question says dinitrogen oxide, which we know as the laughing gas, N2O, has been used as an anesthetics in dentistry since 1844. Under certain conditions, nitrogen and oxygen react to form dinitrogen oxide, N2O. Suppose that you are a chemist attempting to prepare N2O from N2 and O2 for use in dentistry. You need to know the expected equilibrium composition. You plan to transfer a mixture of 0.482 mole N2 and 0.933 mole O2 to a reaction vessel of volume 10 liter, where it will form N2O at 800 Kelvin. At this temperature, the equilibrium constant for the reaction is 3.2 to the power of minus 28. Calculate the partial pressures of the gases in the equilibrium mixture. Now, it looks overwhelming, the volume of question. Don't be overwhelmed by it. Just go straight to what you're asked to do. So what were we given? So let's just quickly write what we're given, and it becomes very easy for us. So we can say that the concentration of N2, so what we're given, concentration of N2 is equals to 0.482 mole over 10 liter. And of course, that becomes 0.0482 molar. That's the concentration. The concentration of O2 is equals to how much of O2? 0.933, 0.933 mole over 10 liter. And of course, that's equals to 0.093 molar. So we know the molar concentration. Now, this is the equilibrium reaction. We have 2N2 plus O2 to give us 2N2O. So the question is to calculate the partial pressure of the gases in the equilibrium mixture. All right, we can determine if we write, of course, for this reaction, Kc, or rather generally, for any reaction, Kc is equals to Kp RT minus delta N. Now, in this case, minus delta N, you have, so we have 2 moles of product and 3 moles of reactant. All right, and that will be minus 2 minus 3. Okay, minus into bracket 2 minus 3, and that will be plus 1. Okay, so that's simply equals to, in this case, this is simply equals to Kc is equals to Kp RT. Okay, let's see. Okay. All right, so let's see. So we have said that Kc, okay, let me put this way. Given that delta N in this case is equals to 2 minus 3, which is equals to minus 1. It implies, therefore, that Kc will be equals to Kp RT. Okay, so we have this. Now, why are we doing all this? We want to find out what Kp is. So we can write Kp is equals to Kc over RT. Please bring out your calculator and tell me what Kp is. So Kp is equals to Kc, we're given to be equals to, where is it? Okay, 3.2 to the power of minus 28 over, sorry, R, because we want to take the R in atmosphere, so it's become 0. Okay. That's what stuff is saying. That's like very good stuff to the place. All right, the next code for the attendance, while I want to open on that page, is U3, U as a letter U in capital, U3, T All right. I'm sorry for the slides each there. My fault. I didn't include a page. So, and I need to put the page there. We can solve this problem together. All right. So let's continue. All right. So we have written. Okay. So we have seen that for this reaction, Kc is equals to Kp RT. All right. We can write that Kp is equal to Kc over RT. And Kc were given in the previous slide. To be equals to 3.2 to the power minus 28. 3.2 to the power minus 28. Over R, which is 0.08206. And of course, T in the reaction we're told is what? We're told at 800 Kelvin. 800 Kelvin. That's times. Let's solve this together by bringing out our calculator. So we have, I didn't bring the solution, I didn't give it so that we can solve it together. So it could be a real life experience. 3.2 exponential minus 28 divided by 0.08206 times 800. And here you have 4.87 times 10 power minus 30. 4.87 times 10 power of minus 30. All right, so now we know what Kp is for this reaction. All right, so we can go back to our I's. That's so we have N2 plus O2 to give us 2N2O. And of course, we have 2 here. And we're given, I have to go back again to the next page. Okay, let's go to the next page. All right, we have here 0 points. Okay, sorry, my apology, please. My sincere apology. All right, so we've gotten the, we don't have to put our head with that. We've gotten the Kc or Kp. All right, now let's do this way. So I guess a way to go about this now is that if we can know the concentration of each of them at equilibrium, you can know their partial pressure at equilibrium. So let's go back. So we have N2 plus O2 to give 2N2O, and we have 2 of this. Yes. Okay. Okay. Why doing that? Let's quickly put in the last code for the attendance. Let me quickly write that. A S G 6K, all in capital. ASG 6K. Please, everybody, click that and press submit. And press submit now. Because after 9 a.m. and we are just have 7 minutes more, you won't be able to submit. So please submit now. So while you are doing that, let me continue with my solution. Okay, so we have the initial concentration for N2 is is 0.0482. 0.0482. All right, 0.0482. For this is 0.09333, I think. Let's look at it together. Yes, 0.0933. All right. And of course, nothing here will have been formed. Now, what changes will have occurred at equilibrium? By the time 2x mole of this is consumed, x moles of this will have been consumed, and 2x moles of this will have been formed, such that the equilibrium concentration will be equals to 0.0482 minus 2x for this, and this is 0.0933 minus x, and this will be 2x. All right, so we can say therefore the equilibrium constant Kc is equals to N2O squared over N2 squared and O2. And that becomes, excuse me, please, that becomes 0.0482. Sorry, that becomes, that'll be, that's 2x squared over 0.0482 minus 2x squared, and of course times 0.0933 minus x. Okay, a very easy way out of this problem really is because when we look at the value of the equilibrium constant, you can see it's very, very, very small, as in extremely small. We got a value of minus 30. The implication of this is that the amount of x that dissociated, or the amount of x that has dissociated from N2 and O2 is very, very small compared to their initial concentration. All right, so we can, with that, assume, since Kc is extremely, very, very small, far, far less than 1, far, far less than 1, it can be assumed that 0.0482 minus 2x will be approximately equals to 0.0482. Similarly, 0.0933 minus x will be approximately equals to 0.0933. And if we use that there, we can say therefore that Kc will be equals to 4x squared. 4x squared. Our objective is to get out what x is, divided by 0.0482 multiplied by 0.0933, such that 4x squared will simply equals to the product of this multiplied by Kc that we have obtained previously. And let's see what it's going to give us. The Kc that we're given, rather. Okay, and that should be equals to 1.439 times 10 raised to power minus 30. And so therefore, x squared will be equals to okay, because of time constraints, because we are already running out of time, x is simply equals to, let me just write, x is simply equals to 6.0 to the power of minus 16. Now, since we know what x is now, it now becomes easy to know the partial pressure because we now know the concentration of each of them. And of course, we know partial pressure. Don't forget. So what I want to leave with us before we go is that we can say here that the concentration of N2O at equilibrium will be equals to 2 times of this, and that's 2 times 6.0 to the power of minus 16. Please note that. So you can do that before the next class. O2 is simply equals to 0.0, like I said, 0.0933. It's going to be very, very, if you remove x from that, you're going to simply get your 0.0933 molar. And of course, for the N2, you're going to get 0.0482. Why did I say that? It's because this x is very, very small. Of course, this x is very small. And the reason why it's very small is because the equilibrium constant is extremely very small. So with this information at the back of our mind, we can now say for each of them, you can say for N2O, the partial pressure for N2O is equals to, don't forget this is CIRT. So you know the concentration, so you can know the partial pressure. So the same thing you go do for the remaining species. And I think with this, we'll have come to the end of our discussion on equilibrium constant in terms of partial pressure. In our next class, starting from tomorrow, we look at equilibrium in solution. Or well, rather, we start with type of equilibrium, and then we look at equilibrium in solution. Thank you. All right, so thank you very much. Okay, please, while you are still in class, please submit the attendance now. Please kindly submit the attendance now. We have just 10 minutes to do that. Please submit your attendance now. So we're about to clean up what is on the board, what's been displayed. I hope you to write as much as you can. Okay. For those of you still writing, we're giving you the opportunity to round up the writing so we can wrap it up. I was actually going to solve this. So it's supposed to solve it in their own. I just took some of it. So that's why it's okay. Significant as in All right, so I'm wiping up the slates, and I want to believe it should have been done with submission of attendance now. All right, so we continue in our class 9 a.m. tomorrow. 9 a.m. tomorrow. Thank you. I'm going to join your senior colleagues to celebrate convocation. I'm sure convocation rights are waiting for you. All right.